Chapter 13, Sustainability and Recycling. This chapter is all about where stuff comes from, how long does it last, and what we do with it after we no longer want it. Several ocean currents passes each other while moving in different directions in the North Pacific Ocean. This results in a huge spiraling circle of water continuously moving clockwise that covers an area greater than the state of Texas. Plastic trash and other debris entering the sea from land are swept up by the currents into the North Pacific Gyre. About 20% of the plastic made around the world each year ends up in the ocean. Plastic in the ocean biodegrades down naturally into smaller and smaller pieces, but the process is much slower than it is on land. Plastic in the ocean is swallowed by fish, seabirds, and other ocean creatures. Worldwide, people recycle only about 10% of the plastics that are produced. The use of plastics is unsustainable because it cannot be maintained. Sustainability is a broad term that refers to the capacity to endure. To make the use of plastics sustainable, we can recycle 100% of our plastics so that we can dramatically reduce the amount of new plastic made each year, or to create plastics that are less durable. Plastics that would break down more readily would not persist for decades. Either solution mentioned here would increase the ecosystem capacity to endure. A life cycle assessment, or LCA, can help to determine the sustainability of a certain product. The figure below shows the life cycle of a manufactured product. Most products that we buy go through this type of process to reach a store. Raw materials are harvested and make their way to a factory, where they are made into something. That thing travels to a store where you buy it, take it home, and use it, and ultimately discard it or its packaging. Finally, many products go to the incinerator. A life cycle assessment accounts for the energy and the materials that go into making a product and disposing of it. This type of investigation is sometimes called a cradle-to-grave analysis because it tracks a product from its raw material, the cradle, all the way to its disposal, the grave. The figure on this slide shows the LCA for plastic cups. A plastic cup is made from oil. The oil that is extracted from earth is made into plastic, and the plastic is made into cups. The cups are distributed to warehouses, and then to stores where consumers buy them. In each of these steps, energy is consumed and waste is produced. The used cup usually has one of the three fates: incineration, a landfill, or recycling. The LCA is not just a way to determine the cost of a process, but also to determine the environmental impact of a product or process. The table below summarizes some of the environmentally relevant findings for the manufacture of plastic and paper cups. The manufacturing process for both cups requires significant electrical power. Both processes use natural resources, such as crude oil and wood. They both contribute to pollution. The plastic cup has a higher carbon footprint, meaning that the production of one plastic cup releases high levels of carbon dioxide into the air. The production of the paper cups also causes pollution, but the paper production pollutes water more than air. Plastic cups have a relatively low biodegradability compared to paper cups. The cradle-to-cradle design describes a product made of a material that can be reused in different products at the end of the original product's lifetime. An LCA can also take into account the sustainability of plastic versus paper cups. Plastic cups are made from an unsustainable resource. The fossil fuels exist on Earth, and as time goes on, they are increasingly difficult to find and extract. Any product that relies on fossil fuels and is not conscientiously recycled is unsustainable, because the raw material is in finite supply. A sustainable process does not deplete a resource. Rather, a sustainable process uses resources that are part of a cycle. Sustainability relates to more than just raw materials. It also relates to the end of a product's life. Product manufacturers lately are thinking more about what will happen to their products when they are ready to be discarded. Nike recycles sneakers and dismantles them into rubber, foam, and fabric components to make Nike Grind. To make Nike Grind, the sneaker company grinds up the shoe parts to create a premium-grade raw material with many innovative applications. It is an ideal component for high-performance Nike footwear and apparel, as well as high-quality sports surface, including courts, turf fields, tracks, and more. This is a real-life example of cradle-to-cradle design. Plastics are made from polymers. In chemical terms, the prefix poly means many. They are many small organic molecules called monomers, connected together in a head-to-tail fashion to form a long chain called a polymer. There are no hard and fast rules about how many monomers must be linked together to constitute a polymer. Although most polymer chains contain at least 100 monomers and often many thousands. Polymer chains can be long or short, branched or straight. Their physical properties are also vary widely. Some polymers are tougher than steel. Other kinds of polymers are stretchy, water-resistant, biodegradable, or even antibacterial. The figure below shows some everyday items made from polymers. Natural rubber is made from a white liquid called latex from a tropical tree. Its primary component is polyisoprene. The figure on the right shows the latex strips from a Hevea brasiliensis tree. The complete structure of polyisoprene is drawn in a circular way around the figure, so it fits onto the page. But the structure is flexible and so can be drawn in different ways. The structural formula contains a motif that repeats over and over again. This motif is highlighted in yellow, called isoprene. The brackets around the isoprene structure indicate that the isoprene connects to itself, end to end, at the points where the brackets are located. The subscript 36 indicates that the monomer isoprene is repeated 36 times. Quite often, we don't know how many times a monomer is repeated. In that case, the number is not indicated. Instead, we write the letter N to show that the monomer unit is repeated many times. The structure of a polymer often determines its physical properties. Recall from Chapter 4 that covalent bonds can range from very polar to nonpolar. Hydrocarbons that contain only carbon-carbon bonds and carbon-hydrogen bonds are quite nonpolar. Therefore, like most hydrocarbon polymers, polyisoprene is a highly nonpolar polymer. Compared to polyisoprene molecules, water molecules are extremely polar, and because their polarities differ, polyisoprene and water repel one another. Because of these properties, polyisoprene makes a good waterproofing substance. This type of polymer is described as hydrophobic, meaning water-fearing. Not all polymers are made only of carbon atoms and hydrogen atoms. For instance, a soft contact lens must be accepted comfortably onto the surface of the eyeball. From this aspect, we need to design a hydrophilic polymer. The term hydrophilic describes a substance that attracts or mixes easily with water, or simply say water-loving. The figure below shows a hydrophilic polymer found in some contact lenses. The hydrogen atom of the surrounding water molecule interacts with the oxygen atom from the polymer, and the oxygen atom of the surrounding water molecule interacts with the hydrogen atom from the polymer. All of these interactions are through hydrogen bonding intermolecular forces. This type of interaction between the polymer and water makes the polymer hydrophilic and guarantees that it will interact easily with water. It will not repel water like rubber does. In addition, a contact lens should also be flexible because it needs to conform a person's eyeball. From this consideration, the polymer must be flexible with a bendable backbone that is similar to natural rubber. To achieve that, the backbone of this polymer is made up entirely of carbon-carbon single bonds. On the other hand, polymers with double bonds are usually less flexible. Polymers can also be designed for rigidity and toughness. DuPont chemists developed Kevlar in the 1960s. Kevlar was rigid enough to pack together as crystals, in much the same way the ions in solid salt packed together into a crystalline lattice. As shown in the figure below, it contains an alternating pattern of bending rings, which make the polymer less flexible, and a special grouping of atoms that contain one carbon atom, one nitrogen atom, and one oxygen atom. This functional group, known as an amide, is highlighted in yellow. The bond between the nitrogen atom and the carbon atom in the amide group is relatively inflexible. The amide bond and the benzene ring together made Kevlar polymer very rigid. The polymer flexes very little, so each strand is relatively straight. And because of the strands are straight and rigid, they can pack tightly together to make a regular three-dimensional crystalline matrix. When they pack together closely, the individual strands of this polymer interact with one another via hydrogen bonds. These hydrogen bonds, which are shown with orange dashes in the figure, act as cross-links between strands and make the material even stronger. In this polymer, they occur between amide groups on neighboring strands, as highlighted in green color in the figure. This three-dimensional crystalline structure gives the polymer extraordinary strength. In fact, Kevlar is 5 times stronger than steel. It is used to make cables for suspension bridges, bulletproof vests, protective helmets, and sails, among other things. A highly ordered crystalline region in a polymer is called a crystallite. The more crystallites a polymer contains, the harder it is, and the more resistant to external influences, such as increases in temperature. For example, the number of crystallites in a given volume of the relatively rigid polymer, called polyethylene, is much larger than the number in the same volume of the liquid polymer known as polymethylcyanoacrylate, the polymer in superglue. From the given structures below, the polyethylene streamlined structure allows for the formation of crystallite structures in the polymer. In contrast, the branching groups in polymethylcyanoacrylate get in the way of one another, making it difficult for its polymers to pack into a regular repeating crystallite form. The structural features of a polymer often determine whether that polymer can readily be recycled, which we will explore in the next section. We can categorize plastics as thermoplastic polymers or thermosetting polymers. When heated, some polymers gradually change composition as the energy supplied by the added heat breaks the crystallites apart and changes them to more fluid regions that lack specific shape and odor. The lower the percentage of crystallites in a polymer, the more pliable and more malleable the polymer is. When it cooled, they reform crystallites and therefore retain their new shape. On the other hand, a jet engine manufacturer would need a thermosetting polymer that will maintain its shape when heated. By definition, thermosetting polymers are extremely tough polymers that do not change shape when heated. Bakelite is an excellent example of thermosetting polymer. Most of the plastic things we encounter every day, including plastic forks, cell phones, pens, and cases for contact lenses, are made of thermoplastic polymers. If we heat one of these atoms, it melts and its crystallites will become fluid. The fluid mass can take on a new shape and retain the new shape when cooled. The ability to manipulate thermoplastic polymers makes them recyclable, meaning we can use these polymers again and again. In contrast to thermosetting polymers, thermoplastic polymers are easily reshaped and reused. The word thermoplastic means heat moldable. Therefore, all thermoplastic polymers are capable of being melted, but this doesn't mean they all have the same melting point. These differences in melting point can also be exploited to create polymers that serve different purposes. The 6 thermoplastic polymers that make up most modern plastics are listed in the table on the next slide. In the first column of the table for each entry is a number known as Resin Id Code. These codes indicate how easily a thermoplastic polymer melts and therefore how easily recycled each polymer is. The numbers range from 1 through 6, where 1 indicates the most readily recycled. Note that LDPE and HDPE are two polymers that have the same monomer but different resin ID codes. The difference between the two is in how they are manufactured. Two different manufacturing methods produce polymers with two different densities. A miscellaneous category Resin ID Code 7 includes other thermoplastic polymers and plastics that are a blend of more than one polymer. Because most municipal recycling programs allow residents to deposit all their used plastic items in one container, the first step at a recycling facility is usually to separate everything into the 7 Resin ID Code categories. Once the items have been separated, they are sent to a chipper, where they are cut into small flakes that are then thoroughly washed to remove contaminants and labels. After the flakes have been sterilized, the sterile, label-free plastic in each category is sold to a plastic manufacturer, who then melts it down and reforms it into some new shape. During the 1980s, only a small percentage of people in the US recycled plastics. The process was time-consuming because no central infrastructure was in place to collect and handle plastics for recycling. Today, most cities in the US have recycling programs, and non-recyclers are in the minority. The success of recycling effort can be attributed in part to legislation at the state level, requiring that rigid plastic containers to be manufactured with a certain minimum percentage of recycled plastic. States like Wisconsin, Minnesota, Michigan, and North Carolina do not accept recyclable materials in their landfills. San Francisco is the city that recycles the most per capita. As recycling rates increase, it is not uncommon for the plastic in a container to be used 5 times. The plastic in a shampoo bottle may well have been part of a motor oil container or a soda bottle in a previous life. And because the raw material for creating thermoplastic polymers is petroleum, when our demand for plastic decreases as a result of recycling, so does our dependence on petroleum. Recycled plastics are being used in innovative ways to make new products from old plastic. Patagonia, one of the first US companies to use recycled plastic, makes a fleece jacket. Each jacket is made from about 25 recycled 2-liter plastic soda bottles. Patagonia will take back that jacket from a customer who is done with it and use it to make new plastic items such as e-book reader covers. Also, the Eco-Arc building in Taiwan is built from 1.5 million recycled plastic bottles. The building's purpose is to encourage recycling in a country where the recycling rate is only 4%. Lastly, Sherwin-Williams now has a paint made in part from recycled bottles. As a bonus, this paint has low levels of volatile organic compounds. The vast majority of the plastics we use are recyclable and have a Resin ID code of 1 through 6. But unfortunately, even though most plastics could be recycled, only about 10% of them are recycled in the US. The rest go to the landfill, are incinerated, or make their way into the ocean. At the landfill, those non-recycled pieces of thermoplastic polymers can survive in the environment for decades. Plastics with Resin Id codes from 1 through 6 are not sustainable because they usually come from petroleum. If they aren't recycled, they make their trip from the cradle, the petroleum, to the grave, the landfill, or the incinerator. During the incineration, plastics undergo a chemical reaction that degrades the polymer into smaller molecules, including carbon dioxide and water. Carbon dioxide produced in this process contributes to global warming and climate change. Incineration can also produce extremely toxic compounds, such as dioxin, a molecule that damages the human immune and endocrine systems, and is linked to various cancers. For all these reasons, today the push is to design new polymers that are biodegradable. When a polymer is biodegraded over time, its chains are broken and smaller pieces result. If the process continues long enough, it is possible to convert the polymer back to its constituent monomers, or still smaller molecules. The structure of a polymer dictates its biodegradability. Let's compare two very different polymers, polypropylene and polylactic acid, PLA. Polymers that degrade most easily have vulnerable places in their structures. Recall from Chapter 4 that bonds within organic molecules can be very polar bonds or very nonpolar bonds, or anything in between. The bonds between two carbon atoms or a carbon atom and a hydrogen atom are quite nonpolar. Because the bonds are nonpolar, nowhere in the molecule is there an excess of charge or a deficit of charge. When an organic molecule contains heteroatoms, which are typically oxygen, nitrogen, or sulfur, these atoms pull electron density towards themselves. Thus, when one of these heteroatoms makes a bond to a carbon atom, that bond is polar. For this reason, the presence of such an atom in an organic molecule can make that molecule vulnerable to attack by another polar molecule, such as water. Polypropylene has a Resin Id code of 5. It is found in everything from food containers to car parts to packages and labels. Polypropylene is a hydrocarbon and possesses no heteroatoms in its structure, where degradation might easily be initiated. In general, hydrocarbon polymers are inert to chemical degradation, in contrast to polymer chains that contain heteroatoms. But over a long period of time, perhaps millennia, the carbon-carbon bonds indicated in yellow in polypropylene break when exposed to sunlight. Polylactic acid, PLA, is a plant-based polymer or bioplastic that can be made from corn, tapioca, or sugarcane. These plants provide the monomers that join to make the PLA polymer. The structure of PLA includes several oxygen atoms. Each oxygen atom pulls electron density from surrounding atoms towards itself. This means that the carbon atom shown in green is electron deficient and possesses a partial positive charge. Because opposite charges are attracted to one another, the partially positive carbon atom is vulnerable to attack by molecules with a negative charge. In nature, the oxygen atom of water molecule is often the attacker. Recall from that the oxygen atom in the polar water molecule carries a significant partial negative charge, so it can attack the vulnerable carbon and cause the polymer chain to break. The polymer chain then degrades. Because PLA can be broken down easily, it is a highly biodegradable polymer. It is also a sustainable polymer because it comes from fast-growing plants. Moreover, PLA is recyclable. It has a Resin Id code of 7. Question 1. How much of the plastic made around the world each year ends up in the oceans? A. 1%, B. 10%, C. 20%, D. 40%. Please pause your video here. The correct answer is C. 20%. Please refer back to slide number 2 for information. Question 2. What are the steps in the life cycle of a manufactured product that is not designed from cradle to cradle? A. Raw materials harvested. Product made in a factory. Product sold. Take home for use and discard. B. Product sold. Take home for use. Discard. Raw material harvested. Product made in a factory. C. Product made in a factory. Raw material harvested. Product sold. Discard. Take home for use. D. Product sold. Take home for use. Discard. Raw materials harvested. Product made in a factory. Please pause your video here. The correct answer is A. Raw materials harvested. Product made in a factory. Product sold. Take home for use and discard. Please refer to slide number 4 for information. Question 3. How has the mass of plastics at landfills stayed pretty much the same over the past few decades? A. The mass of plastic at landfills has not changed because there are less plastic products on the market. B. The mass of plastic at landfills has not changed because people are using less plastic products. C. The mass of plastic at landfills has not changed because the population is increasing. D. The mass of plastic at landfills has not changed because of lightweighting, which reduces the mass of plastic in a container. Please pause your video here. The correct answer is D. The mass of plastic at landfills has not changed because of lightweighting, which reduces the mass of plastic in a container. Please refer to the nature box in this chapter for information. Question 4. Dismantling old Nike sneakers into rubber, foam, and fabric to make Nike grind for playground surface is an example of blank. A. Cradle to grave. B. Cradle to cradle. C. Waste to grave. D. Waste to cradle. Please pause your video here. The correct answer is B. Cradle to cradle. Cradle to cradle process describes a product made of a material that can be reused in a different product at the end of the original product's lifetime. Question 5. What are polymers? A. Polymers are made up of small organic molecules called monomers that are connected to form long chains. B. Monomers are made up of large organic molecules called polymers that are connected to form short chains. C. Polymers are made up of small organic molecules called monomers that are connected to form short chains. D. Monomers are made up of large organic molecules called polymers that are connected to form long chains. Please pause your video here. The correct answer is A. Polymers are made up of small organic molecules called monomers that are connected to form long chains. Please refer to slide number 10 and 11 for additional information. Question 6. What do hydrophilic polymers contain, such as those used in soft contact lenses? A. The polymer contains oxygen atoms that can interact with water via hydrogen bonding. B. The polymer contains oxygen atoms that can interact with water via covalent bonding. C. The polymer contains carbon atoms that can interact with water via hydrogen bonding. D. The polymer contains carbon atoms that can interact with water via covalent bonding. Please pause your video here. The correct answer is A. The polymer contains oxygen atoms that can interact with water via hydrogen bonding. In a hydrophilic polymer, the hydrogen atom of the surrounding water molecule interacts with the oxygen atom from the polymer, and the oxygen atom of the surrounding water molecule interacts with the hydrogen atom from the polymer. All of these interactions are through hydrogen bonding intermolecular force. This type of interaction between the polymer and the water makes the polymer hydrophilic and guarantees that it will interact easily with water. Question 7. Why Kevlar so strong? A. They are strong covalent bonds in the carboxylic acid functional group. B. They are strong covalent bonds in the amide functional group. C. There is cross-linking between amide groups in the polymer. D. There is cross-linking between carboxylic acid groups in the polymer. Please pause your video here. The correct answer is C. There is cross-linking between amide groups in the polymer. Hydrogen bonds are the strongest intermolecular force. The individual strands of Kevlar interact with one another via hydrogen bonds. These hydrogen bonds act as cross links between strands and make the material strong. Question 8. Which plastic is the hardest to recycle? A. High-density polyethylene, Resin Id Code 2. B. Low-density polyethylene, Resin Id Code 4. C. Polyvinyl chloride, Resin Id Code 3. D. Polystyrene, Resin Id Code 6. Please pause your video here. The correct answer is D. Polystyrene, Resin Id Code 6. The Resin Id codes indicate how easily a thermoplastic polymer melts, and therefore how easy a recycled each polymer is. The numbers range from 1 through 6, where 1 indicates the most readily recycled, and 6 is the most difficult one. Question 9. The bioplastic PLA is more readily biodegradable than a polymer such as polypropylene because they are blank in the PLA polymer structure. A. Crosslinks. B. Hydrogen atoms. C. Oxygen atoms. D. Covalent bonds. Please pause your video here. The correct answer is C. Oxygen atoms. Hydroatoms make polymer biodegradable. Oxygen, nitrogen, and sulfur are common hydroatoms in the polymer. Question 10. Refer to the life cycle analysis of plastic versus paper cups in Table 13.2. Select the statement that is true. A. Compared to a paper cup, the plastic cup is more biodegradable, has a smaller carbon footprint, and has a higher contribution to water pollution. B. Compared to a paper cup, the plastic cup is less biodegradable, has a larger carbon footprint, and has a lower contribution to water pollution. C. Compared to a paper cup, the plastic cup is less biodegradable, has a smaller carbon footprint, and has a higher contribution to water pollution. D. Compared to a paper cup, the plastic cup is less biodegradable and has a large carbon footprint and has a higher contribution to water pollution. Please pause your video here. The correct answer is B. Compared to a paper cup, the plastic cup is less biodegradable, has a larger carbon footprint, and has a lower contribution to water pollution. Please refer to slide number 6 for information.